Whoa, hello there. Wait, I forgot to turn on my camera. Whoa, hello. Wait, no, wait. Here we go. Alright, so the Steam works. Great. I don't get why is this printing it here, but let me just close terminal. And hey guys, it's me again after a long while. It's been a while. Let's just get straight to the content, shall we? Let's just open terminal, projects. I've been working on this for quite a while. It's called mfio, and it's basically going to be this fabric for memflow for when in the future. So it's an async IO framework, and it's going to let you do really cool stuff. And I could go into the details, explain it, but it's a lot of work. It was a lot of work. I laid out the first idea 6 months ago. I've been thinking about it for years actually, and it's best to show. So it's what do we have? mfio bench, open target, base, report, index. Okay, so this is a benchmark suite for mfio, and let me just drop a cheeky add to the stream on the Discord. Let's see. Here we go. Okay, so this is a benchmark of file reads, sequential, reverse, and random. I have a 16 gigabyte file on a remote machine, and the idea is, can we read it fast enough? So just to show you, sequential reads. This is logarithmic scale, and this is not input size in bytes, this is latency. So this is 1 millisecond latency right here. This is 10, and this is 100. So every step it's roughly doubling, not exactly, but roughly doubling. If we go exactly, there are the latencies. So it's 1 millisecond to 5, 10, 20, 50, 100. And there are three different ways to read files. There is the basic standard library, which is fully sync, and it just goes through the file, seeks to a particular position, and it reads bytes. Simple enough. Then there is glom.io, which is a really nice thing. It's completely based on IO Uring, the new hotness of Linux. So it's async. And it's the similar deal, except I'm able to generate a list of futures that will read the file at these positions, while potentially happening out of order, because I don't care about the order, I just need things to be fully read. Is that right? So this lets you issue multiple reads at the same time. And then we have this mfio, which is my thing, and it's same deal. You've got a synchronous for loop. I mean, this is synchronous. It generates a list of asynchronous features, which are then polled concurrently. And the results for sequential reads are roughly the same. There's just like noise, basically. But it gets interesting when you go to reverse. And by the way, this is all, the way I have it set up is I have a Vagrant VM which sets latency of the machine to specific values, and then I connect through SMB Samba and perform reads on the file. So it gets really interesting once you have reverse, which is sequential but in reverse. Standard library, it dies. So if we were to go to sequential and look at the throughput charts, you can see this is reaching 1 gigabyte. So like 1,000, that's 1K. This is 10K. Is it? No, this is 1 megabyte. This is 10, this is 100, and this is 1 gigabyte. So if you read in reverse, you're losing 10 times of performance from the get-go with IO-Uring. It's absolutely insane. But if you go with a standard library, you lose like extra 50 times. So it's like, if you go up to sequential from standard library in reverse, you have 50 times performance gain from switching to IO-Uring, but then you're still 10 times slower than reading it in sequence. And it was really surprising to me because turns out random reads are not that different from sequential. It caps out at 100 megabytes, same as here, and it drops off to 10 kilobytes. It's actually, okay, it's slower. It gets slower. And my hypothesis is, what if, and basically, mfio is completely generic IO framework. I need to lower the music, it's distracting me. I will do that, and I will raise the volume here. I think that should be good. Okay, so mfio is a completely generic IO framework, and a file system is defined file system is basically a trait that has open file, and it returns a file handle which basically implements read and write. That's all it is. So currently we don't have listing or whatever. I focused on the core fabric of a file system, that is of file reading, and that is writing and reading files at whatever position you wish for. So we have this native file system, which is basically a list of different backends, and it works really well, as you saw. But over network, it's still going through the same SMB kernel interface, which for some reason loses 10 times performance when you go in reverse. This would not happen. This shouldn't really happen on local files. I could possibly enable local files and test that. mfio bench. So input dev urandom of equals sample.img, block size 1 gig, count equals 16. So while that's happening, my theory is that on local files, this shouldn't be that big of a deal. Like, it shouldn't drop performance by 10x. because local files are near instant. So what if you have a network file system that's able to handle random reads at high throughput and just have a good random read-write performance over the network? That's my hypothesis, that mfio might just beat SMB kernel thing, but maybe not. We'll see. So we need to create a network file system, and we will work here. So we will develop a network FS. Well, that's always fun. No space left on device. I forgot this. And that's an extra 300 gigabytes of space. Okay. I hope this didn't mess up the stream. So we have a 15 gigabyte file. Okay, cool. Good enough. Good enough. Ignore. Alrighty. So we just need to go to and enable local file. So file with strategy. So it's local, and we go to, it's sample.img. I'm pretty sure. So we have this, and we don't have latencies. I mean, latencies are going to be irrelevant because it's constant latency. So cargo run release bench and local. Let's see. Connection refused. Set latency. Okay, I need to basically local bool. Let stream equals if local this should be okay if let sum okay. So now we're going to skip latency. So let latencies equals if local equals if local 1, else latencies iter.copied, and this should be good enough, I'd say. So we just do latencies, I think. Latencies. So this should completely kind of skip this whole nonsense of using latencies, but what do we have? If else. Okay, file with strategy, file with strategy, file with strategy. True. False. Let's see. Okay, now we should be good. So we have, so sequential, we get 900 megs. And sequential glom.io should be same deal. This is like we're capping out at a gigabyte, which is like, okay, connection refused. Why? 137. 137. It's because if local. No, this won't work. Okay, sure. Unwrap. This should be okay. Oh, don't. Okay. Let's see. Let's see. I'm kind of breaking the whole thing, but it should be okay. So we have 900 megs. While that's happening, let's go build network FS. Still, no such file or directory. 157. 157. Dot map unwrap or 0. Sure. Okay, so network FS. There are actually two aspects to it. There's a client and the server side. So the client only needs to have a TCP stream. Okay. Reverse. So we have 500 megs per second. That's still much faster than 100 megs, I think. Yeah, that's still much faster than 100 megs. And random, you're going to have random. You've got a gig, which is weird. So you've got a gigabyte at random, and STD is just dying. STD is just dying. Well, that was interesting. This was really interesting. But the good thing is that we are indeed getting much faster performance by going, for instance, random. This is much better. Like, this is so good. So in theory, network file system should be much better than going through SMBFS. Sorry, not SMBFS. It's like SMB kernel driver, whatever, or CIFS, who cares? So network file system will have one thing, and that is a Unix stream. We'll just actually so network FS. And what do we need from, let's copy it from thread. So we have things right here. So we have things to do. So we need a TCP stream. So use std net TCP stream. So TCP stream is just going to be here. We have stream. And that should be okay. The thing is, mfio internals require you to, basically, this stream will be non-blocking. And mfio internals will this is going to be tricky to do. This is going to be slightly tricky to do without changing some bits about mfio. So let me just show you. But I guess we can start with blocking stream. So mfio has an async executor. Really simple, really basic. This. And there's also this, but we don't care about Windows at the moment. So basically, it just pulls a feature and then issues a poll system call, which blocks until a file descriptor becomes ready to read. And we pass only single file descriptor, which is passed from here, which is passed from here. So here we go. We have this polling handle, which is a waker, is a pair of a file descriptor and a waker. And you can basically read what it does. Effectively, the core idea of mfio is that you build these IO backends which export a file descriptor. They don't even have to do that, but they export a file descriptor which then lets you plug that backend to any other async IO backend and have it work magically. You need only one file descriptor and it works. So the problem is that this is polling for readable. There is data to read. But right here, this stream is both readable and writable, so we actually need to have another file descriptor that returns that, oh, the stream is either readable or writable, and then, only then, wake us up. Or alternatively, I can change this, where is it? Polling handle to also include what are we looking for? Is it, so basically flags, and struct flags is readable, writable, things like that, basically. And backend then exposes, okay, I react to both of them. I react only to readable. I don't imagine any backend that would react to only writable, but it's a possibility. So I think that's what's going to be needed for mfio to be better. It's so great to do these experiments because I keep finding these small issues. But for now, we're just gonna do it in blocking way. Who cares? Absolutely nobody. So network FS. We're also going to need use stdio self read write. Those are the things we're going to need. So pub fn try new, and we're going to need a socket address. Socket address. And we're going to return IO result of self. And this is a to do. Does that sound good? I don't think we're going to need these. So, what are we gonna have? Yeah, we finished that. What are we gonna have? What are we gonna have? We're gonna basically connect. Equals connect. Let's, okay, I see why we don't have completion. And here we go. Now that's better. Okay. So we basically connect. And that's all we have. So a file system needs to implement two traits. Actually three traits. And if you go to here, you see everything that's being implemented in this enum dispatch. So we have IO backend. We're going to expose this file wrapper, which has these traits implemented. And that's all we need. So we're going to copy from here. Yes. So okay, we cannot format this because okay, let's just delete these. Okay, so what are all of these functions? So IO backend is basically this thing. You get a polling handle, which is that file descriptor I mentioned. We're going to be blocking for now, so we return nothing. Get backend is this function that drives all the IO. And we will need to have this. We will need to have this. Then you have file wrapper, which is going to have stuff inside, and it's going to be a struct. And so basically we mark this as to do. It has these two functions, separate thread state. This is going to be removed, ignore it. It was an idea that doesn't make sense. Try new ID. Try new ID. This is important. This is what allocates kind of packets to the users of the IO system. And you have these two traits, packet IO with these parameters, which is, this is a permissions. This is wrong, right? This is wrong. We cannot read as, can we do this? Yeah. Okay. So yeah. Here we go. So this is a struct. which implements packet perms, which is basically describes type constraints on packet operations. Basically, these are permissions that you can do on the data that's sent to the I/O system. So packet I/O with write permissions allows the I/O system to write data into a packet. So usually write permissions mean the user wants to read the data. And packet I/O with read permissions means usually the client wants to write data to you. And yeah, so you need to implement both of them because these are like separated. And what this usually is, if we go to thread implementation, what this usually is, you have this read stream, which is complicated type. You have a manually drop of manually drop isn't that needed though, I think. I don't think that's needed. Yeah, I don't see why manually drop is needed. But basically, but this is for file wrapper. Oh yeah, because you're implementing I/O on a file wrapper. It's basically a stream, which is a provided type, which basically is this storage pool, a memory pool for user requests to come in and go. And the idea of it is that this is much higher performance than allocating everything on the heap every single time. So this is not really a requirement to use packet stream, but usually this new packet ID is going to originate from the stream. And I think actually this actually requires a stream all the time. Packet stream is needed, such as mfio. So you're basically always having this no matter what. So we're just going to copy these. We have no threads. We're going to copy all of these three. File wrapper. And we're going to skip the manually drop part because I don't feel like we need it. Let me just double check my backend. Yeah, we don't need that at all, actually. So yeah, great. So maybe we should oh, I think we need this for file wrapper specifically because we want to join these threads, and maybe I guess we could write a handler, a wrapper for the thread handle that joins them automatically, but we need to ensure the drop order. Basically, we need to first drop these streams, and only then we can stop the threads. That's the idea. So we don't need this at all. So we have this file wrapper, which stores inside this file inner, which I guess we'll need to look for similarities here. We're going to have this key. So the idea is this, my conceptual idea of the server, of client-server communication. Let me just open draw the painter. So my conceptual idea, client-server boundary. what is this nonsense? You have client server. We connect. Let's use this. We connect. I don't know, basic thing. So we're going to have an open request. We're going to send a message. Open. The server does its thing, its magic, and returns us a ID. Like a U32 ID, which is unique per client. Like this ID is for our files. So the server is going to have a mapping of IDs per each client, so as to not circumvent permissions. You're going to get this ID, which corresponds to the file you just opened. So every time you want to make a request to read files, read the data, you're going to send, say, read ID. You're going to have read ID, and so you're going to read a specific ID, and then finally other data like position, length, and then backend. Something else is missing here. Because you need to also somehow identify the packet ID. So this is going to be packet ID, which is generated by the client. This is by the client. And then the server is going to return the results, which are going to include the packet ID. So this is going to be right here. Yeah, you don't need this ID because you have a packet ID. But sure, we're going to return ID, and I'll mark this as a question mark because this is probably not needed. And then you're going to have position, but this is not position. This is going to be index into the packet. Pretty sure. Yeah. Index into the packet. Length. And you're going to have a buffer that's of the size length. This is the worst drawing ever. And that's a whole protocol. And the backend is going to do processing, do its magic. It keeps track of these associations. If a client disconnects, you just free all the data. Who cares? And the client just needs to keep track of this ID. So a file inner, there is no file inner because you're just going to have a file ID. That's all there is. And you're going to have this read stream, write stream. Yeah. Try new ID. And try new ID. It's just going to be this. Let's just double check all the permissions. So read stream has write permissions. Yeah. That's all we've got. And that's basically it about the file wrapper. And then we're going to push stuff here, I think. Okay, is there something else missing? Or are these streams per file? Yeah, this is a stream per file. Okay, cool. So notice how we're actually doing it. So we're creating a yeah, we have this CTX. And this is what we're actually going to need. We have this IO ops handle, which is bound to a key. It's bound to a file ID. And let's go to this IO ops handle. We're going to need this. We're going to need this. All of this. This is what we're going to need. This is another part of chain. That packet stream is kind of opaque, if I may. So IO ops handle. They have the packet IO handle. I think that's what's static, and you're going to have file ID, and you're going to have the state, which is netfs state. Netfs state. We're going to have file ID. File ID. Okay, so you have the handle. This is boilerplate. This is kind of, this is not boilerplate. This is where all the packets come in. You see, you have a packet. You have a packet, and we basically push. We're not going to do this stuff here. We don't need it. So we have we need to implement this pushing. Hey, Jorksa, how's it going? Hey, Crystal, welcome. Yeah, it's been a while. Okay, so this is not native FS. This is network. Okay. So we're going to have a internal struct, netfs state, and netfs state is actually going to hold the stream, basically a stream state, and it's going to be a arc, base arc. So it's going to be base arc mutex of netfs state. And if you're confused, why do we have this base arc? It's Tark, my crate, really cool stuff, transposable, type erasable, and FFI compatible arc. It's really helping for MFIO's use case. So you have a stream. Let state equals base arc new mutex new netfs state stream. So we have the stream, and we need mutex, which will be parking lot. Yeah, I'm just doing copy paste, and I love this. So we have this. Okay, so the pattern I came up with that works really well is this into op, which converts a packet to an internal operation, and it works really beautifully. So this is what we need here. We need to have an into op trait, but we basically need to figure out how are we basically what the operation is going to be. So we're going to have struct operation. So there's enum operation. And what do we have? So we don't need to allocate anything at the moment. We're just going to have a bound packet. So you have two operations: read bound packet static with write permission, and write bound packet static with read permission. So that's the core operation that we have. And so it's op type. So we're going to have file ID. File ID position u64, although this could be anything. For now, let's start with u64. And type op type. And this is all we have. And this is generic. We're just passing it through. There's no other magic happening. So in this place right here, we don't need into op at all, because all we're doing, although no, yeah, we need to match this. Okay, we need into op trait. So it's going to be very simple. Into op. And this is what you have. So we're going to have file ID. Okay, we don't need anything. We're going to return op type into op for read. So it's not, no, this is packet. Bound packet. I think we ran out of music. Let's try again. Okay. It's gonna be loud, so yeah, watch out. Chat. I'm gonna play this again and it's gonna start off really loud. Oh no, it remembered. Okay. Okay, so we have bound packet. And this is all that's going to be. This is going to be write packet. So, done. That's all we have. And this is going to be read. That's all we have. Where self packet perms. That's all we need. Beautiful. Okay. So we have into op. We don't need to do anything here. So let operation equals operation file ID self dot file ID pause and into op perms into op packet. That's all we have. So we create this operation, which we then push. We're going to push on a queue, which is in the netfs stage. Ops is going to be deck of operation. So we just do state.ops.push back operation. That's all we have. I'm pretty sure. So ops is default. So collections, you use std collections deck. We don't need thread stuff. We're not going to need this or this. We might need these. Okay. And now we have it compiles, but it does nothing. Now we push packets onto a queue. We need to process those packets now. This is where a backend comes into place. So, backend. This is what you have. Backend container. And this is what you have, this monstrosity for Mio, which is a non-blocking backend. Really beautiful stuff. And you're just going to put backend here. Okay, I was missing something. Okay, yeah, we need this. Okay, that's good. That's good enough. What are we missing? We don't have Paul. Okay, we need Paul. So we've got this, but we need to get rid of this part. Okay, so we lock it here. We lock the state. So now we need to implement the meat of the system. We have a TCP stream that can read and write stuff. Great, wow. And we need to pass messages back and forth. How are we gonna do this? Isn't it? And by the way, later we may replace this with just like a generic input read plus write. Wouldn't that be cool? But for now we have a TCP stream. But wait, I need to no, I think it's not separate. I wanted to check if stream could be split into read end and write end. Although let's still check. Rust TCP stream. So these are the docs for TCP stream. we need TCP no delay. We need to set no delay. Although no, we would manually flush. We would manually flush. So it's okay. Okay, whatever. So So what is happening here? Let me explain this loop. What is a backend? I think structure fields. What? Wait a second. So what is a backend? Backend is this loop. It's still not super well defined. I have some problems with the current design, but it's an async feature. It's a feature that is in a loop. And the current idea is you have a block which processes all the IO things that it currently can process. And then it goes to sleep. And it goes to sleep in this really stupid way, which is basically we just return pending once. And next time we will continue. And this seems like it could be replaced with just this bit is needed, and then you handle this implicitly. But basically, currently, this is the core setup. This processes outstanding events, and then it goes to sleep, and then it gets awoken whenever there are more events happening. Currently, we're going to work with a blocking TCP stream, meaning we will never in theory, we should never need to be awoken. Everything should happen in a single poll. Well, not exactly, but a finishing of IO request automatically wakes this async function up, so you have this recurring thing without the need to be woken up by a file descriptor. So right here, we need to basically process every single outstanding operation. So while let sum op equals state.ops.pop. So we have an operation and we need to serialize it on the network. So we're going to have an enum message type, and we're going to have read 0, write equals 1, and we're going to have open file equals 2, close file equals 3. Or I guess open and close. But let's be explicit. Or be file open and file close. I think we're going to have just up to 256 commands. Like if we implement the entirety of standard library, let's just take a look. Rust stdfs. So this is file system. This is all we have. We have copy, which is like just a shorthand for opening, reading, etc. You have directories, create there, etc., etc. You have read there, which has extra things. Read link. You have some shorthands. Remove file, rename, set permissions. Symlink, write. So I don't think there is a chance we're going to have more than 256 commands. So this is what we have. We're using a single byte to represent a message. File ID, usize, it's going to be actually file ID U32. You could make a case, maybe U16 should be enough, but whatever. This is the minuscule thing. We can pass a U32 every single packet, no problem. So if we consult our handy chart, we need to send to the server. We're ignoring open, by the way, currently, because it's going to be complicated to pass it. We're just going to send this message type. We're going to send ID of the file, and we're going to send a packet ID. So we're going to allocate a packet ID. This is something we need to handle. We're going to have position and length. So we need to have this in progress packet. In flight ops. And it's going to be a slab, I think. Yeah, it's going to be a slab of in flight op struct in flight op. So actually, or do we even need it? No, we do need it, because this is what we're going to have. Packets, packet shards. Whoa. We're going to have a B3 map of U64 and okay. In flight op. U64 and a bound packet. Sharded packet. Now you may be thinking, what the hell is this? So, one of the core things of mfio is that packets, everything can be fragmented. So, whenever you perform an operation, you may get results out of order. You may get results out of order. And you're going to have to split them up. Basically, that's the idea. And that's kind of the idea of it. So you have a single packet ID for the whole unit, but you're getting results back in chunks. And those chunks have the position attached, basically. That's at least the idea of it. And yeah. So we have this in-flight ops. It's going to be struct in-flight op. So we're going to have a file ID. No, we don't need. In-flight op. Read sharded packet. Write sharded packet. Read. That's kind of the idea. We need B-tree map. And we need a slab. So, in-flight ops. So this is going to be pop back. Do we need? Yeah, no. Or I guess, could I just have in-flight op here? You know, would be certainly fairly simple, I think. Let's actually just replace this with in-flight op. Well, in-flight op. Okay, and we're going to have basically a from implementation for a sharded packet. From bound packet static terms for sharded packet terms. From, and we have packet bound packet static terms self, and we're just going to have self shards once. We're going to just have 0. That's all we have. We're basically writing a packet at 0th position. So this is usize, actually. This is going to be usize. And yeah, and we're creating a op type, which is basically a sharded packet. Boom, done. So what we need, all we need to do is for op type do message type. And match self message type read self write message type write. So we're going to have a message type. Oops, this needs to be like so. And we're going to have So we have a message type, and we need to write the message. So equals message type. Okay. So we first write that. We are going to need file ID. Let file ID equals op.file ID. I mean, we don't need to do this, but this is going to be simpler to just get these out of the way. So we need position, length. Oh, we need packet ID. So we're gonna get so we're gonna get position. We're going to position len equals we're going to get the length here. And we need a packet ID. So we're going to do let packet ID equals state dot inflight ops dot push, I think. And we're going to push this operation, I think. Yeah. So this is, I think we need we actually need packet ID at the end, just so that we can push an in-flight operation right here. Once we've written the packet out. I think that's the idea. So like if you have a write operation, you're going to write the packet contents, and then you're gonna end with packet ID. Think that makes sense. Think that makes a lot of sense. And if you have packet ID at the start, you need to do this dance. That's kind of stupid. It's going to be pretty simple if you do it in this order. So we don't need this. Isn't that great? Although, would remote file system need to, okay, it allocates either way. I think it allocates either way. I think it allocates either way. Oh, my camera died. Oh, let's see if it turns itself back on. Yeah, and it's back on. Great. So, no, actually the backend doesn't need to allocate. Nah, it does need to allocate. So what you're witnessing me is figuring out if I need to allocate or not. I think I need to allocate, but I don't necessarily have to. What I could do is just read directly off of the stream but that makes it sequential, very sequential. But if there was a way to just fill in a buffer, if you could, so this is the cool thing about mfio. If you could have a buffer you could store the you could just read on a circle into a circular buffer the contents, and you have a size limitation of the write operation, and you don't copy it anywhere else. Don't copy it anywhere else, and you're just holding on to that. You're just holding on to that operation until it's done and you release the back elements. But now thinking that's probably a bad idea, because what if you have chained network file systems, the order is gonna get wacky. No, it's probably better to allocate a buffer for a packet. Here's the data. Boom. Here's a box that you can split up. Easy. And then you just let it go. Once all of the packets are processed. I think that's the way to go. I need a break, so I'll be back in a bit. See ya. Okay. Well, let's continue, shall we? So I actually believe it's not that hard to get us the packet ID, just in case. It's really not that hard, because all we need to do is slab. We need to just query it ahead of time. So vacant entry. That's what we can do. We could, yeah, think. And that's what we're going to do. So, according to this stupid diagram, we need packet ID here before position. So we could get it at the start. Equals state dot inflight ops dot vacant entry. Let entry. Okay, so before pause, add packet ID equals entry dot key. As U32, because yeah. Assert entry dot key less than U32 max, less or equals, as it says. Okay. So we need the length operation here. Self read okay, and we need to implement length here. fnlen size. Okay. Okie dokie. I just realized that usize length may not always make sense, because maybe length should be in the position units like U64, and it should be a range, and you should just OOM if you can't process that large lengths. But that's a problem for another day. So we just need to get the position of the last shard and get the length of it. So let some packet equals solve the shards last. Okay. L0 pound packet. We need to implement use splittable, but we do cargo build. We can re-import it here. Okay, so it's actually so we don't need this. Can't leak private type into op. Okay, sure. Trade. We don't need it public. So this is Rust Analyzer spazzing out. Let's see. Huh. Let's explicitly import. No splittable in packet? Wait. What do you mean? It exists. This is peculiar, but okay. This is the first time I'm having a bug in Rust Analyzer. Interesting. So we don't need that because it can't find it. I wonder. Yeah. Okay, so this works. So we need to write these. We need to write these into a stream. Okay, so suppose we wrote that. We need to actually put the package into the in-flight hubs. Now, while thinking, I realized what I'm doing with sharing the pre-flight and in-flight hubs may not work, because right here we will be writing the packet into the stream, and that consumes its data. So actually you have two types of ops, pre-flight and in-flight. So we're just going to op type So this is fine. Well, this type is fine. These functions that are implemented on this type are fine, but in-flight ops are going to be in-flight op type. In-flight op type, which has a sharded packet, that's fine. Except here we're going to have bound packet, static, bound, no, this is correct. This needs to be changing. Bound packet, bound packet. Okay, so we're going to transform bound packet into a sharded packet. Except once again, the sharded packet, if it's a write operation, it will be so-called maybe allocked, meaning we've read the packet out. We've read it. We've seen its data. And we're just waiting for confirmation. That's it. So this sharded packet of being just a bound packet, that doesn't work, does it? Instead, we're going to have T splittable. Going to have a T splittable, and that's going to be a T. And read operation is going to have a bound packet of this, but this is going to be maybe allocked static read. That's the idea. I feel like Rust Analyzer is spazzing out because it's just like living on another planet. It's just seeing the old version of this. But yeah, so maybe allocked is this monstrosity, which is ugly. It's ugly. But basically it's either an allocated packet, which we can just access, or it's a bound packet, but we have the buffer somewhere else. Yeah. Think so. No. This is the type we need to alloc or transfer it. Yeah. So we have suggestion, but it's messing up. This is really peculiar. This is really, really peculiar. So we have this. Splittable is not implemented for perms. Ah. Yeah, this should work. Okay. Packet perms is not implemented for T. Ah, we need to do from T. And I think we're good. We're golden. Okay, we're good. Jesus, guys. We keep going through the music. Damn. The stream is long. And I don't think we'll finish it today. Because we'll get halfway. We'll get the client done, I think. But then I'll call it a day and then continue tomorrow. I really want this to be done. So we have splittable. And now the idea is we have the entry. We have message type, file ID, packet ID, position length. We need to write these to the stream in order. I guess we could just do strict. It depends. So let's try to define this as like an enum message. No, it's a struct message type, message type. And then you match message type, the message type tag, to the actual message type. So read has a few things. Read has okay, we're going to use union. So it's an untagged union. So because we're separating these because we need to actually read the tag, etc. Or we could use Bing code. No shade. We could use Bing code. Potentially. Can we just use Bing code? It would be interesting. Can we just do that? Define an enum that does all the magic. And what if we just use Serde? You know, so Serde has, okay, so we have postcard. Is Bing code like out of date? Why is, you know, why is Bing code not in Serde list? I mean, okay, so compact encoder decoder pair that uses a binary zero fluff encoding scheme. Same or smaller? I think we should I think we should just use Bing code. Ah, so it's not Serday. Will almost always be encoded as U8. Okay. Okay. And you know, you could use postcard. This is nice. We've got variant. So what do I use? We could just could just use Serday, or we could use Bing code. So Serday would give you a bit more flexibility in terms of, okay, maybe you want to switch to a better format. You know, maybe. But maybe not. Anyways, let me say. But okay, I think it's the same. Yep. I'd say just use postcard. More flexibility. So Serday version equals 1 not features equals derive, postcard equals postcard version 1. Yeah, version 1. So we will need to feature gate this. Yeah, I'd say we just define this. So message. Rust induces brain lag sometimes. Sometimes. So read is going to have packet ID. This is going to be U32. I guess we could use variant, but yeah. We're going to have ID. File ID. Packet ID. Position. 64. Length. Length of usize. Right is going to be same thing. File open, going to have file name. File close, file ID. This is what we're going to have. This is what we're going to have. And now the only thing is that write will also at the end put the whole packet contents. That's the idea. I'd say, yeah. While read will just send this over the wire. Cool. So we do derive serialize, deserialize. So use serde, deserialize. And we're going to use postcard. What are we going to use from postcard? From bytes and so we have from bytes. We're just gonna read. Can we use reader and writer? Or do we have a feature flag that's missing? Maybe we're gonna use bin code because we want to just write directly and read, you know. So if you go to docs.rs bin code, you're going to have bin code read deserialize. So this is bytes. Deserialize from reader. Yep, we're gonna switch to bin code because bin code equals 1 because we need the readers and writers. It's so strange that we don't have postcard reader writer. That sounds so wrong. Deserializing from TCP stream. sounds horrible. This, yeah, bin code. Bin code it is. Bin chilling. Okay. Bin code, encode, decode. Okay, so we're going to have messages. And we're just going to have fn write self packet ID and we're going to have destination this is what we're going to have. So we're going to do op.write so operation you have file ID, etc, etc. Okay, so you need these as well. Okay. So we have destination, we have file ID, we have position, and we have packet ID. If you have all of this, you should be able to create a message. Equals match self read message read file ID pause packet ID self write and we need length. Okay, so we get the message and we're going to write this message. What does the project do? Okay, so mfio is just this abstract IO framework that's concerned about being async, fast, low latency, high throughput, and good for random access. So you have these packets that you send and you can fragment into smaller pieces. And I've been working on it for quite a while, and it's proven to work quite well for I/O that you just do for synthetic I/O tests and for local file I/O tests. And even if you go through NFS, SMB, it works pretty well. There are benchmarks right here. And what I want to do is so this is using this file system implementation that's sitting on top of IO Uring or EPOL, whatever it's available. And it works in line with glom.io, which is based on IO Uring, so it works in line with that. But this 100 megabytes per second speed of random reads, that's 10 times slower than sequential reads, which are 1 gigabyte per second. And I'm trying to see if, okay, can we go ahead and just create a file system implementation of mfio that skips SMB, that skips the local file system, that skips the kernel's file system handling, and instead just goes directly to the other end and asks, okay, could you please give me these bytes at this position? And my hypothesis is that we're going to have increased random performance, and as latency increases, we're going to have less of a drop because we're pushing more ops through the pipe, and it doesn't matter when they come back. It can be half a second later, so long as the pipe is read, processed, it should be okay. And we should saturate more, and we should see less of a drop as latency increases. And mind you, these benchmarks are slightly misleading. Input size, it's not bytes, it's latency milliseconds. So this right here is 1 millisecond, this right here is 10 milliseconds, and this is 100 milliseconds. And yeah, all of this is logarithmic scale, so if it looks a bit funny, I just don't want things to be stretched too badly. So like this drop is actually more substantial than it seems, but I want to see comparisons, not just like fancy graphs. And yeah, so that's the idea, and I'm making this networked file system, which is lots of ugly code, but it's actually like 260 lines currently, and I think it's going to be like 100 more for the client. And then you're going to have to write a server, which is going to be another like 500 lines. So 1,000 lines total, and you should have a file system implementation over the network that works really well. Potentially. I really hope it does. But I don't know. And also, Rust Analyzer is spazzing out. Because let's just clean that up. Nice. Cargo build release. And yeah, it should now be refreshed, up to date. So where we are at, we got this packet to write. So we're going to turn operation. The conceptual thing we need to do is let in-flight op equals op write, and we're going to send state.stream, And we're going to unwrap because we want to panic if something fails for now. Later there will be this whole process of making it asyncable, etc., non-blocking. It will be a bit tougher, so the code will grow, but for now we're just assuming the simplest scenario. So we create this op, and then we do entry.insert in-flight op. That's conceptually what we want to do in this loop, and we're going to hide this write. Behind this function, which is going to be operation. Yep. Operation fn write. So it takes self and is going to take a destination IO write. IO result. So self. Okay, and we need one more thing, and that is packet ID. And that's U32. So here's that. And one more thing, we need to actually put it here. Entry.key as U32. Return type of this call is due to the argument passed. So we need to return in-flight op type. Oh no. In-flight op type and to do, because okay. So we're going to do call right here, and it takes destination, file ID, pause, packet ID, file ID, pause, packet ID. File ID, pause, TY. We're gonna destruct it right there. File ID, pause, packet ID. And I think that's all we're going to do here. That's literally all we're gonna do in this function. In-flight ops type. And we're taking a mutable reference to this. Destination, right. That's kind of the idea of it. Right. Let's change this into right MSG. What's the problem? It's an associated function, not a method. So that's so weird because okay, self. Let self Okay, here we go. And that should be compiling roughly. Okay, so we need bin code. Repository. Okay, do we have examples? Bin code. Okay, so we're missing a feature. Feature flags. Wait. So it should be, or is this? Do we have v1? Oh. Okay, so bin code in v1 is 30. Okay, so my memory is correct. We actually need 30. So 30 equals version equals 1, features equals derive. So use 30, serialize, deserialize. Okay, that should work just fine now. Second mutable borrow occurs. State as mutable. Okay. Can I do this? Okay, that works. Beautiful. So we're just storing a mutable reference here because we don't care about the locks tied. Right, so we compiled. Now, what else? I actually need to write the message. So we're going to do bin code serialize into. Serialize into. Okay, well, my camera died again. Overheating is fun. Thanks, Muppers. Glad you're enjoying it. So I hope there is more cool stuff is coming along the way with this mfio stuff. So serialize into destination. Okay, well, the camera is dying. We're going to live without the camera for a bit because it's severely overheating. Although, wait. Screen cam. No, disable camera. Okay, I'm sorry. That's unfortunate. We need to let it cool down a little bit. That's like a running issue. Let me. It's really toasty. Maybe there's also a problem that I forgot to open up the flap that so the display was right next to the camera instead of being extended. But oh well, I should get like a fan or something for the camera, or just get a different camera that doesn't overheat. But so we need that, and we need value, which is MSG. Wow, guys, MSG. So what's the result type? So what's the result serialize into? And what's the result? Is there a way to contact me? Oh god. Bin code error. Yeah, is there a way to contact me? Discord, I might reply. Email, it's on my website. Hey Dank, good to see you. Why does this box? So box error kind. Okay. So. If let encode error kind IO equals E, else error kind other document. Okay, that works. So we serialize into, and now we need the final part of writing these messages is to actually write the packet. See you, Muppers. Okay. So we need, this is where we're going to transform operation type, the bound packet, into a sharded packet. Write packet into this. So if you go, so this is going to be that match self read. So read is going to be simple because we're just converting in-flight op type read. In-flight op type read. But if it's right, we're going to do more stuff because we actually need to write the packet. And writing the packet is done in two steps. First step, you try to allocate the packet, because in mfio a packet is not necessarily allocated. It can be generated on the fly. This is the thing that will allow you to take please read me entire 64-bit address space and then actually don't have a buffer for a 64-bit address space. It would just allocate on demand as there are results ready. So that approach is really cool, I'd say. But if you're writing stuff, you may be like, okay, I want to write to the entirety of 64-bit address space, and I will allocate on demand when you actually have stuff ready. Or I will actually just generate the data and write it to the destination once you have a location ready. So mind you, this is kind of breaking on this network layer. This writing to the entirety of 64-bit address space is currently going to be broken because the network layer, it just pushes data. So it doesn't know how much on the other side is going to be fragmented. But on the read end, it's going to get fragments back. So yeah, right. Let's write data. So first, so we're just going to check a thread implementation, alloc. So we're going to do try alloc. We need to match against, well, match try alloc. So okay. So this is allocated packet. So we're going to just write the data here. But if we have error, we get back the bound packet. And we need to do here because we're going to do let equals that in flight op type right. This is what we're going to do. Okay. What happens if we have a read packet, allocated packet? Let's try to so what happens if we have a read packet? We're just going to do test dot write all. This is all we're going to do. Okay, beautiful. So we write all, and yeah, that's about it. Now here, this is where we need to employ a temporary buffer. So we're going to need to have temporary buffer, maybe on an edge of U8. And this is what we need here as well. This is what we need here as well. And we need to have that temporary buffer in the netfs state. And this is going to be right here. And we're going to pass it right here. So this is persistent store. We're still, no, we're not compiling. Okay. So this compiles. The final bit we need to do, let me just turn on the camera. Okay. So hopefully, yay. Okay, so we have this temporary buffer, which we can use to allocate. We need to do limit allocation size, but we're going to do this. if temp_of.capacity is less than packet length of.reserve and minus temp_of.capacity, right? And we're going to temp_above.set length. Set length to b.length, and this is unsafe. The safety of this, the data here is uninitialized. This is safe because we have maybe uninit. It's okay. Now we actually need to transform that data to initialize data, and this is gonna be funny. Oh no, it's okay. Unsafe. It's okay. It just uses unsafe. Transfer data. As PTR. And we're just gonna return error. Beautiful. That's, I think, it for this. Python Finance series. How come? That's certainly an idea, but why would I be qualified to do that? You mean like trading? I mean, maybe. I'll keep that in mind. Safety. Temp of has enough capacity for the packet. So if you just note safety, the caller must ensure that input pointer is sufficient for the bounds of the packet. In addition, the data pointed by input must be properly initialized and byte addressable. Well, properly initialized. This requirement. AI trading bot. I'm skeptical because you can't just put data into AI and have it figure out. It's millions have tried, millions have failed. Very few have succeeded, and those who have succeeded are working for big quants. So I don't have sufficient machine learning knowledge to do that. That said, there is a cool thing I have that has potential. I just never got around to finally actually doing it. So I might try it out, but I can't say because A, it's gonna kill motivation, and B, it's I need to see if it works first. Okay. I think 2 hours 30. Yeah. Guys, we're going back to the same music from the start. I need to get more. I need to have like 3 hours more music than I have currently. Where was the stream? Okay, here we go. All right, so technically the client should have everything needed. We don't even need the length. So that's what we have. we write data. You know, we write the data, and we've completely written the packet. Now we need the results. The results are going to be interesting. But you also have got the server that needs to be written, the server side. And the results is like, once you have the server, you can write the results. So I think it would be an okay spot to stop. I will... Associated function is not used because I don't have open. Let me do... Let's see. Ow. Wait, what do we have in git diff? Okay. We can add... So git branch netfs. So, git checkout netfs git push. You can see the code on GitHub. It's been quite funny. I have the repo. Here, the code is fully public. Yeah, this is CodeCov. CodeCov is like spazzing out a lot. Like it just goes up and down. Although it went down because I added more file systems, right? That's expected. So here's mfio. It's got 37 commits. Feel free to check it out. And it's a really cool repo because it's very clean and stuff, and it's even like, let's check actions. Look how much CI we have. We have 8 different runs of Miri. 8. With different random seeds. Those are meant to catch race conditions like that are randomly skipped. So like 8 is sufficient usually for those race conditions. And what else? You have lints for different OSs, tests, etc. This is tested a lot. But yeah, what have we done? I started working on this really... Where is it? We have file system. And I've added this bit. This bit is done. What we'll need to do, we need this, which is opening files, parsing open files, actually performing IO. Jesus. And let's draw it like so. Okay, now I fixed it. Okay, it's a bone. And actually receiving the results back. So next time we'll focus on this bit, the server side. And once we have that, we'll add this, and then – and then we'll do the file opening which is funny that it is that way, but this is a beautiful drawing. I don't know, this is the best. And so it will take a bit, 3 hours or so, but it shouldn't be too hard, I think. So yeah, what can I say other than it feels good to be back. Thanks for watching, and I hope you understood something, and I hope this was useful, and I hope I see you maybe tomorrow, potentially. I have a social life now, so it's, you know, but we'll see. Anyways, thank you very much for watching, and don't forget to overflow the like button. See ya.